Greetings and salutations, magical chemists. Let's talk about Half-Life in all of its glory. First, just a quick reminder that there are two different types of rate laws we can use to determine the order with respect to a given reactant. The differential rate law is the one where you have a data table that's going to contain information about the concentration and the rate. And then you just compare the multiple trials when you look at one reactant held constant and you're changing another and you see what it does to the rate. The other type of rate law we have is the integrated rate law. That's the one where you're given a data table or a graph containing concentration and time data. This is the one where we use what we call graphical methods, where you compare the three different graphs: the graph of the concentration versus time, the natural log versus time, and the reciprocal versus time, to determine which one is most linear, and that will determine the order with respect to that reactant. Now remember, as far as half-life is concerned, all orders of a reaction have a half-life, but the only one that is tested is the half-life of a first-order reaction. That's why this formula shows up on your formula chart. You just have to remember that it's there. Okay, let's talk about what half-life really is. Half-life is officially defined as the time it takes for 50%, or 1/2 of the original reactant sample to disappear or get used up. Okay, as I mentioned, the AP test focuses on the half-life of a first-order reaction. That's honestly because they are simpler. They are the only ones where the length of the half-life is constant regardless of the initial concentration. But I should be specific here. It's constant at a given temperature. So half-life will change if you change the temperature, but it won't change if you change the concentration of reactants. And so the only equation we're going to need to worry about as far as AP is concerned is that the half-life, or T1/2, that's what half-life is 0.693 divided by K, the rate constant. All right, so let's go ahead and take a look at a graph of the change in concentration of a first-order reaction over time. Well, notice it's first order, so this is not a linear graph. But you can check at the initial temperature, at the initial time, you have 100% of your sample. So if you're starting at a concentration of 1, sweet. After exactly one half-life, you have decreased to exactly half of your starting concentration. After 2 half-lives, you've decreased to 1/2 of that. This is why, according to half-life, you almost never reach 0. It just gets really, 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 really small. So 3 half-lives later, now we're down to, even tinier amounts. So graphically, remember, this is not a linear expression, but the half-life, the amount of time it takes for the concentration to decrease by half, is constant. So let's try a practice problem. Okay, so a certain first-order reaction has a half-life of 20 minutes, and I want to know the rate constant. Well, I think you'll need a handy-dandy formula, straight from your formula chart. So, of course, my half-life is 0.693 divided by K. Make sure that's a lowercase k. We're not talking equilibrium here. So, and they told us that that must be equal to 20 minutes. Well, that makes it nice and easy to go ahead and solve for my rate constant. Because if I rearrange that algebraically, I can see that the rate constant is just equal to 0.693 divided by 20 minutes. So not only does it give me the answer, it gives me the units. So my half-life is pretty tiny, 3.47 times 10 to the negative second inverse minutes for my rate constant. Okay, so now it says, okay, that's great. How much time is required for this reaction to be 75% complete? Well, 75% complete means only 25% of your reactant is left. Well, let's look at this. If I start off with 100%, of course, whatever I have, and then when one half-life passes, I'll have only 50% left. And then if another half-life passes, only 25% will be left. Well, 25% remaining is 75% complete. So this reaction must need to run for 2 half-lives. Well, I know one half-life was 20 minutes, so 2 half-lives must be 40 minutes. And that's it. That's about as complicated as it's going to get. So I know there's a specific formula that you can use when you're like how much time versus how much half-life, how much is left. You shouldn't need it. This kind of like rough calculation be like a 1 half-life, 2 half-lives. This is as detailed as you will need for AP Chemistry. All right, let's try a practice problem. Yum! Hey, look at all this pretty data. Oh, look, they're graphing concentration, natural log, and the reciprocal. I wonder what we might be expected to find out. Well, first, we want to know the order of the reaction with respect to N2O5. I guess to be fair, that's the only reactant, so we win. So we want to write the rate law expression and justify your answer. So you should totally pause the video and try this on your own. Now, if you have a calculator, you can graph this data, but you don't have to. This is something that you could be expected to do without a graphing calculator and still be able to answer this question. So see what you think, try it, and when you are ready to check your answer, unpause the video. Well, you may be wondering how the heck you're supposed to figure out which graph is most linear without actually graphing them. Well, you just have to look at the distance between the data points, because notice the time is increasing at a consistent amount of time. So you're looking for something where there's about the same difference between each consecutive data point. So let's do a quick check. Well, if you look at the concentration versus time data, you notice that there is not a consistent difference between the data points. They're getting smaller and smaller. So this graph is clearly not going to be linear, so it is not 0th order. Let's check the next one. So we look at the natural log data. Well, if you check these, I mean, they're not exactly the same, but they're pretty dang consistent. So this is a good shot for possibly being linear, but just to be safe, let's double check our reciprocal data. Well, this data is clearly going up. So this one is also not a constant change when the time change is constant, which means this is not a linear graph either. So the only one that could be linear would be the natural log data, which is why this must be a first order. So now we have to go ahead and explain why this is. It is totally okay to say that it's because a graph of the natural log of the concentration of N2O5 versus time will be linear. Even if you didn't actually graph it, we can tell it would be linear just by looking at the change. Make sure when you're explaining this, it's not enough to say, well, the graph of the natural log will be linear. No, you have to say the graph of the natural log versus time will be linear. That part's essential, because otherwise they're like, what are you graphing it versus? You have to be specific. And did you remember to say it would be linear with a negative slope? Remember, the AP test always includes that phrase on their answer key. I'm still not 100% sure why, but it's a thing we have to say to get credit, so that's what we do. And so, if you want to justify that, you could say it's shown by the approximately constant rate of change in the natural log of N2O5 every 25 seconds. But you don't have to. This is enough. Okay, so once we've got that, we can go ahead and do part B, which says, hey, what's the value of the rate constant, including units? Guess what? This is something you totally know how to do. So you should try that. And then, if you know the rate constant, I bet you can find the half-life. So you guys should totally try parts B and C. When you're ready to check your answer, well, of course, unpause the video. Okay, to find the rate constant, did you remember to take the absolute value of the slope? I absolutely hope so, because if you did that, then you're just picking 2 points and plugging in numbers. Remember that slope is the change in y over the change in x, so for us, that's the change in the natural log divided by the change in time. So just pick 2 points, and you'll get pretty much the same answer. I like to pick the first point as one of mine, just because, it's always going to have a value of 0 for something, and that just makes subtraction easy. All right, so now we just plug that in, we get a number, and, oh, I forgot my unit there, because this also gets us the rate constant, it gets us the rate constant, but also the unit for the rate constant. So you end up getting a pretty tiny rate constant of 0.0080 inverse seconds, which means now that we know the rate constant, it's easy enough to use our equation to find the half-life. Since we know the half-life is 0.693 divided by the rate constant, well, we just need to plug in our rate constant. And so we only have 2 sig figs here, but that will give us a half-life of 87 seconds. What's nice is that we can always look back on our data and see if this matches. So let's go backwards to our data. Well, if we look, so notice, they made it easy for us. We started at initial concentration of 1 molar. So our half-life is going to be somewhere in here, right? Well, that should be somewhere between 75 and 100 seconds. And in fact, look at that, it was. 87 is totally between 75 and 100, so that's a good sign that we did something right. And so did you, ta-da, because now you've learned all about Half-Life. So you are ready to collide head-on with the glories of chemistry by moving on to the next video on collision theory. I'll see you there.